Hi, I'm Nikolai Vasquez. Some of you may know me for some of my work in the Rust community, specifically the static assertions crate, my most popular library. I've been doing a lot of interesting things with Const recently, and that's what I'm going to share today. So, the answer to the question, how powerful is Const? Const is very powerful. Thank you very much. No, don't worry. So what you came here for is why is Const powerful, not just that answer. So let's start off with what exactly is Const within Rust. So Const values are immutable, compile time evaluated, and they can compose with each other because you can use consts within other consts. And the underlying tool that enables const to work very well is called MIRI. And MIRI stands for the Mid-Level Intermediate Representation Interpreter. And what that means is that Rust gets converted to this representation that is easier for the compiler to deal with. And it's easier to evaluate because it gets all the semantics and it doesn't need to do extra work that the Rust C front end already did. And this is very similar to how a lot of languages work. So mir then gets converted to LVMIR. This is the same way that Swift works, where Swift also has an intermediate representation that gets converted to LVMIR, and then that gets converted to machine code. So the most basic usage of const would be, say you have arithmetic like 1 plus 2, and then this would just evaluate to 3, and then anytime you use n, it would be as if you just put 3 there. And so you can use const to do things like initialize statics, where the difference between a static and a const is that a static is a runtime value that has a specific address, and statics can also be mutable. Consts can never be mutated. Const can also be used as a parameter to a type. So in this case, an array type. So we see that we have 3 values, and so we can say, oh, this is an array of n, which is 3. And similarly to arrays, more recently, Rust has adopted const generics, and what that enables is you can pass in const values and have, for example, in this case, we have the myGeneric type, which you can have any size array, but the size needs to be known at compile time. And so here we have let g is myGeneric, and we're specifically saying this needs to have an array of length 3 on the inside using the lovely turbofish syntax. And similarly to before, we have our array of 3 values on the inside. But const can do a bit more than that as well. So you can also have logic and loops. So here we have, we're basically computing 2 to the 10th power, which is 1024, but using a loop. So this is relatively recent as far as I've been using Rust is concerned, but I guess it's been a while now. Const can also do compile time assertions. So in this case, we are saying that we want to run the assert macro at compile time. And if the assertion passes, then there's no value to be returned, and so we use the unit type. And if we don't want to have this symbol lying around for the assert, we could just use underscore, which is a wildcard, which basically makes the const anonymous. And so most people who have been doing Rust for a while will be familiar with this surface level usage of const. So static values, assertions, converting enums to integers, loops, const generics, which I just mentioned, and const defend, where you can wrap logic in a function that can be evaluated at compile time, as well as associated constants on types. But there's a little more to const than what most people know. So you can do a couple interesting things as well, such as concatenating slices or parsing integers or transcoding strings from UTF-8 to UTF-16. And such a case where you might want to be transcoding strings would be, for example, say you're interoping with Java, C#, or Objective-C. those use UTF-16 as their native encoding. And so if you want to be efficient with strings that you know at compile time are just going to be passed into those languages directly from Rust, then you could just convert at compile time those strings to UTF-16. And so the specific example I'm going to cover here is concatenating slices. So say we have a string stir here, and we have our string howdy. So if we wanted to be able to pass this into C, what we'd want to do is append a null byte so that C knows this is where the string ends. And sorry, the strings are different here, my mistake. But the issue here is that you need access to the string literal, and so that doesn't really work if you want to be more general and be able to work with any const. And so if we wanted to work with any const, what we would want to do is be able to concatenate a null byte. And so the way we can start off with this is we can take a slice of the string's bytes and then encapsulate some logic in creating a C string. So given the bytes of, given the string and its, because of issues, I don't have my speaker notes, so I'm kind of ad-libbing right now. Given that you have the, you want to convert to a C string, what you want to do is append a null byte, and so you want to create space for that null byte because static values already have a specific space allocated, so you can't just mutate the existing string. And so what we can do here is we create new const bytes with space for just one more byte for that null byte. And then once we've created those bytes, we can then convert them back from UTF-8. And if we want to be safe about that part, then we can have a checked conversion. And as I mentioned before, you can have panics at compile time. So we can just stick the unreachable macro there. And as the name implies, that code shouldn't run. You could also use from UTF-8 unchecked here if you're very confident with what you're doing here. And so the way that you could approach appending that null byte is you can create a wrapper struct that contains the data of the string that you want, and then followed by that space for the null byte. And we can guarantee that the null byte will be at the end by using repr_c. And for those who don't know, repr_c essentially ensures that the struct has the same exact memory representation as if you wrote that same exact struct in C. And so in C, the order of the fields need to be the order that you present them in. So in Rust, the optimizer is allowed to rearrange the fields if it notices that, oh, this struct might end up being smaller if we put certain fields higher up or lower because of alignment. And so given constructing this null byte, we can provide data by taking the string's pointer and then converting that to a pointer of the U8 len array, and then dereference that pointer. So just read straight from that pointer that we just casted. And then null, we just put 0 there because that's what we end up wanting to do to make C happy. And given that append null is guaranteed to be the same size as a buffer of len+1, we can then transmute that just to a raw byte array. And this will give us the layout that we want as a contiguous array. And this is essentially all the code you actually need to do string or slice concatenation. It can specifically, I've seen it mostly be used for adding nulls for C strings, but this generalizes pretty well. You could have this have types of T that are copy and then concatenate slices of that, but this is a specific instance that I've seen this used most often. And so these are some of the more advanced features that you can use with const that you're probably not going to be reaching for often, or maybe you just never even encountered a situation where you'd want this. But for some of us, we end up dealing with this, And not just this, we end up dealing with some cursed const. So it gets worse than that. And so these three crates, they do very interesting things. The const format crate essentially provides functionality similar to the format macro, but available at compile time. The impulse crate lets you check, does a type implement a given set of traits, and you can assign the results of that, the Boolean result of checking that, to a constant. And the way it works under the hood is also using constants to make that work. As well as there's another crate, con type, which is, I'm gonna go over the implementation of that, that lets you do conditional typing. So what that means is that given a condition of true or false, you can either choose type A or type B. So I will be going over how that works. So consider that you have a function that needs to handle throughput of bytes. And naturally, we deal with slices. And so the length of a slice will be a usize. Usize specifically is a pointer-wide integer. And that is because the memory address for like 32 bits, so in the case of 32 bits, this will be 4 bytes, you can't reference more than 2 gigabytes, so it doesn't make sense for usize to be able to demonstrate a size greater than 2 gigabytes. And so we would naturally use this with a slice, and this works out pretty fine. And so we have this blob of just some data. Doesn't really matter what it is, but it fits in memory, and we want to, say, log the throughput that we're dealing with, or whatever you want to manage that value. But consider that we want to also make this work with bytes that are taken from the file system. And we don't necessarily want to read the whole file at once, because consider you're on a 32-bit system and you have this really large file that's just not going to fit in memory. And so as a result, the file length actually ends up using U64 because the disk can store more than memory can on a 32-bit system. And so you end up having a mismatch between usize and U64. And this is demonstrated by the compiler. It'll nicely tell you, oh, well, you could try converting it, and if it happens to fit in usize, then it passes, but otherwise you might panic if you call this try into with unwrap. And so you may be tempted to, oh, sorry, that's repeated. You may be tempted to change handle throughput to take a U64, and this works pretty well for the most part, but consider a future where we have a 128-bit system. Not that we may necessarily need that anytime soon, but say you really want future compatibility. Or say, this casting to U64, sometimes you use usize, sometimes you use U64, and you might accidentally truncate going from U64 to usize or vice versa. And so we do have these conversions for usize, and we can't just do a from implementation because we see that U32 and U64 are not listed as conversions, and so even the Rust standard library has gone out and said, oh, yeah, this may end up truncating, so we don't want to ensure like this is a lossless conversion. And so we have this conflict of these two types, and we want to be able to represent whichever is the larger of the two, let's use that one. And so on a 64-bit system, these two are going to be the same. On a 32-bit system, you'll end up using U64, and on a hypothetical 128-bit system, you would end up using usize as the greater of the two. And so you could represent this as an enum by having a variant for usize and then a variant for U64. But the issue becomes that you end up needing extra memory just to be able to say at runtime, oh, which one am I using, even though you know at compile time which is the one that you want. And so we could mitigate this by using a union, but that's fraught with its own issues. In order to access, so going back a second, the difference between unions and enums is that enums will tag at runtime which variant you're using, whereas unions are essentially untagged enums, or vice versa, enums are called tagged unions sometimes. And so because we drop this tag at runtime, we need to be sure when we're writing our code, which is the one that we actually want to be sure about using. And that's why you need to wrap this with unsafe to get access to the usize field or the U64 field here. And some projects have forbid unsafe, and this is just not a solution. Also, you now have another type that you're dealing with, and so that can get clunky, and so you're probably going to have to implement methods on it to say, oh, from usize or from U64, and then handle that in a pretty awkward way. And so there's a way to make it so that we can represent usize 64 as either U64 or usize. And we can do this depending on a generic constant. So here I have a trait called proxy, where I'm trying to get access to this associated type, U64. And we can implement this trait proxy on the unit type just to have something to implement it on. And so we can say that when pointer is greater than 64, let's use usize, and then if it's false, let's use U64. And so this ends up working fairly well, actually. And you can have your condition of, oh, if usize is greater than U64, then you can end up getting access to that associated type that will end up being usize or U64, depending on that constant. And this is really clunky. It does get us to where we want, but this is really weird code to look at. It's not really the best maintainable thing, and you're not really gonna want to have to say, oh, unit as proxy is greater than U64, usize 64, just to be able to be dynamic at compile time over whether you're using usize or U64. And so we can actually assign a type alias to the results of this. And then we can just make it that we just use that type alias going forward. And because we have either usize or U64, we can just use integer literals directly. And we can also make this generic over, I missed a thing, sorry. But we can make this, imagine you have a type alias that has a generic Boolean, and it can end up being the same code as you saw before. It can alias to empty tuple, also known as unit, as proxy usize 64, and then we can alias that as the con type. And so that's what the con type crate does. And it also provides these usize 64 and for other sizes if you want as well. And so going back to our handling of throughput, for example, logging, now when we get the file length or we get a slice length, we can losslessly convert, regardless of target platform, to this function, and we'll always have an integer that's correct. We'll never truncate, and we'll never actually end up using more space than we need. And so those are some of the crates that wrap these very odd and different uses of const if you really want to go that far out there. And beyond that, there's more capabilities that are on the horizon. So there's various features that I think a lot of people are excited for that are being developed. Specifically, const heap will end up allowing allocating vectors at compile time and then essentially creating what would be equivalent to a slice at runtime without doing any runtime allocation because it's at compile time. And another feature that I'm very much looking forward to is const trait impl, and what that specifically means is you can use various traits within const. Right now, it's very limited. Really, the only trait you can use is copy, but that's just saying that you don't need to call clone and it's not move only. So there's no real methods on it. It's just a matter of how the compiler itself is treating the value. And if you really want to go further with const beyond what some of these features that are working towards stabilization are doing, there's a unstable flag called unleash the Miri inside you that enables you to do just way more things with const. However, it's very likely that the compiler will crash on you. And so this iceberg becomes the iceberg. So taking a look back over this, there really is only a certain section that most people are only going to be dealing with, but it's really nice to know that if you have very interesting circumstances, you could reach for these other very unique and different solutions. And so in conclusion, this has been the work that I've been doing. So the con type and the impulse crates are mine, and I'm very excited to see what people can do with const. Hopefully this is inspiring. If you want to keep up with what I'm doing, I'm at Nikolai Mastodon at Hachyderm. My name, Nikolai Vasquez on Twitter. And if you want to subscribe to email updates, I now have a newsletter, which you can check. You can subscribe to at news.nikolaivasquez.com. And I have two fun announcements. I'm working on a benchmarking library that I'm very proud of. I'm hoping to announce it this next week. It's called Divan, so look out for that. As well as I am currently working with Frederick Grevsky, who's right there, helping him make his TrustFall project that enables querying various data resources more powerful and seeing how we can enable businesses to become more productive and just, yeah, it's exciting. So, yeah, that's it. Thank you so much.